first glance, it appears unlikely that we are under threat from extraterrestrial objects. Yet at any moment, the sky could fall on our heads. Our solar system contains millions of objects that we call asteroids. The smallest measure just a few inches across, but the largest can have a diameter of 300 miles. Some circle the sun like planets, while others cross paths with Earth's orbit. To avoid a collision with potentially catastrophic consequences, we need to locate these bodies, understand their trajectory, and categorize them. A vast survey of these space objects is currently underway, since they could end our world as we know it, as they have done in the past. 65 million years ago, the largest animals ever to exist were wiped out when an asteroid measuring 30 miles across collided with our planet. Dinosaurs and 80% of all other animal species were unable to survive the consequences of the cataclysm. Deposits of fine particles found all over the world in sedimentary layers have led geologists to believe that the impact triggered a kind of nuclear winter, plunging the Earth into darkness and interrupting plant photosynthesis for several years. First, herbivores and then carnivores died of cold and hunger. Fortunately, most asteroids are small, just a few inches wide. We see them at night as shooting stars, small asteroids that burn up when they reach our atmosphere. Every day, they add around 100 tons to the weight of the Earth. That's almost 40,000 tons per year. These small particles pose no threat, but when they reach a size of 30 feet across, they become problematic. Just over a century ago, an asteroid of this size brought massive destruction to a remote area in Siberia. In 1908, reindeer herders on the banks of the river Tunguska witnessed the anger of Ushir, their god of wind and thunder. This event remains a mystery. Nowadays, most scientists believe it was the result of an asteroid measuring a mere 150 feet across that exploded 5.5 miles above the Earth. This airburst is estimated to have been 1,000 times more powerful than the atomic bomb dropped on Hiroshima. It was the largest asteroid impact in recorded history. Fortunately, it took place in a sparsely populated area. If it had happened 5 hours later, the rotation of the Earth would have put the entire city of St. Petersburg in the path of the asteroid. The fireball and subsequent blast wave flattened some 80 million trees over 800 square miles. Near the epicenter, trees were charred and stripped of their branches, but remained upright. Today, the vegetation has grown back, and the only reminder is a small lake created by the impact. The Tunguska asteroid escaped detection since telescopes at the time could only pick up objects hundreds of feet wide. Many asteroids have been discovered at the Côte d'Azur Observatory in the south of France, where one of the world's leading asteroid experts works today.
Using an old telescope like this one, the first asteroid was discovered in 1801. Ceres was found at a distance where people expected to find a planet. Little by little, they discovered more and more objects, which were called asteroids, from the word aster, meaning star-shaped.
To understand the origins of these objects, we need to look at the birth of the solar system.
Our solar system was born around 4.5 billion years ago. At the time, our young sun was surrounded by a disk of gas and dust, tiny pieces of dust that started colliding with each other and sticking together to form bigger and bigger objects.
These objects are planets.
Jupiter, the largest planet in our solar system, formed first in the first million years, followed by the other planets.
Most of this dust and gas was gathered up by the planets. But not all.
Asteroids are the remnants of the formation of the solar system, rocks that never managed to come together to form planets.
The closest to the Sun are rocky planets. Mercury, Venus, Earth, and Mars, followed by gas giants, Jupiter, Saturn, Uranus, and Neptune. Like planets, asteroids rotate and orbit around the Sun. By the end of the 20th century, scientists had already catalogued over 10,000 of them in an area known as the asteroid belt between Mars and Jupiter. Other asteroid belts lie beyond Neptune. These rings are usually represented as dense clouds of rocks, but in reality, asteroids are spread out far from each other. Sometimes, asteroids are known as minor planets, but unlike planets, they can leave their orbits at any moment. To explain these deviations in asteroid belts, trajectory specialists need to fine-tune their calculations.
The trajectory of asteroids is perturbed, first of all, by the gravitational force due to the sun, but also that of all the planets. Position of the planets is extremely well known. The problem is that the position of the asteroid is not known exactly because it comes from measurements, from physical measurements, and each measurement comes with an uncertainty.
Scientists also keep a close eye on the trajectories of other celestial bodies, such as comets.
Comets are small icy bodies very rich in ice and unstable elements. So when they pass close to the sun, their ice melts, transforms into gas and creates long tails. They're what we call active bodies.
One thing that comets and asteroids have in common is that their orbits around the sun can cross that of a planet at any time.
The Tunguska explosion in 1908 was not the event that triggered our awareness of the risk of asteroids. In fact, that happened in 1994 when a comet hit Jupiter.
This comet, named Shoemaker-Levy 9, was torn apart by Jupiter's gravity and collided into the gas giant.
It was the first time that humans saw a collision like this in real time using telescopes. It took a concrete event which we could experience ourselves to realize that there were indeed small bodies colliding with planets. And it was on this basis that the European Union made their first resolution in 1996 to deal with the risk of impact.
The study of asteroid risk has become a science in its own right.
Asteroids are in the solar system and they're orbiting around the sun. And from time to time, we have collisions between asteroids that produce smaller fragments. And then we have interactions with the other planets as well. The gravity of these other planets can sometimes inject them into different orbits and change how they're moving in space. When that happens, if one happens to be moving in an orbit that crosses the orbit of the Earth, we call that a near-Earth object.
Fortunately, the Earth's atmosphere acts like a natural shield, burning up small near-Earth objects when they come into contact with it. But the atmosphere doesn't protect us from large asteroids. If one of them fell on a populated area today, it would undoubtedly cause massive destruction and kill thousands of people. There are 50 times more people on Earth now than there were 2,000 years ago, and our towns and cities are scattered across the globe.
If you double the surface area on Earth that's covered by human infrastructure, logically, you then double the chance that an asteroid hitting Earth will impact a populated area. Let's take, for example, Dubai. A few decades ago, there was very little there, and now it's a large, thriving city. And of course, if an asteroid hits a large, thriving city, it's going to cause a lot more damage.
Oddly enough, our chances of being impacted remain small because, despite our growth, humans still only occupy a tiny fraction of the Earth's surface. Since the Tunguska event in 1908, the Earth has only been hit by small asteroids. When an asteroid hits the Earth, it is known as a meteorite. A number of close calls show the potential danger of these meteorites. In 1954, in the United States, a meteorite crashed through a house, injuring an inhabitant. In 1992, another struck the rear of a car. In 2006, a house in Sumatra was damaged. In 2007, a field in Peru was hit, releasing sulfurous gases, and in 2008, a meteorite landed amongst the workers in a paddy field in India. Since the surface of the Earth is 2/3 water, most impacts happen at sea, unbeknown to us. But our cities remain at risk from these intruders from space. Our planet still bears the scars of violent collisions from the past. So the question is not if, but when we will be hit by a large asteroid. To answer this, some astronomers study a celestial body that has circled the Earth for billions of years. The Moon. Since the Moon has no oceans, no atmosphere, and no vegetation, its surface is an open book that recounts its long history of asteroid encounters. And the story continues today. Some astronomers monitor these collisions as they happen.
I started because I had observed the impact of the Shoemaker-Levy 9 comet on Jupiter in 1994. And I started to wonder about the rate of impacts, not only on Jupiter, but in the Earth-Moon system. Then, by looking for impact craters on the Moon, I could measure that impact rate, that flux, and describe the danger for the Earth.
These real-time observations are crucial to understanding the threat of asteroids.
By analysing the craters, specifically the numbers of craters present on the Moon, this allows us to estimate how much cosmic material is bombarding the Moon. We know that over the last maybe 3 to 4 billion years, the flux of this impacting material is approximately constant.
On the scale of the solar system, the Earth and the Moon are very similar. Numerical models regard them as identical targets.
We can then determine how much material is out there and what is the likely impact on planets like Earth.
The number of impacts calculated from the craters on the Moon gives an impact frequency that is fairly worrying.
It now appears that asteroids measuring 3 feet across hit our planet at least 10 times more often than previously thought.
The size of an asteroid that creates a Tunguska-like event, so perhaps 50 meters in size, will happen on average every few centuries. A 100-meter asteroid might hit every few thousand years to Earth. And then even larger scales, 1 kilometer, we're talking every perhaps 500,000 years, but in that case, the consequences are global.
There is a statistical relationship between impact frequency, asteroid size, and the damage they cause. So, asteroid risk is quantifiable.
It's like playing the lottery. We don't know when such a phenomenon will occur, and even if it's not likely, it can happen. And we have to have the appropriate defense systems in place.
The Moon serves as a clear warning. Therefore, astronomers collaborate to create innovative solutions for monitoring the skies. Telescopes remain the most common tool to find near-Earth objects, asteroids that cross the Earth's orbit. But since the discovery of the first asteroids at the beginning of the 19th century, there have been major advances.
When we see an asteroid in an optical image, It appears as a dot or a streak across the image. And with multiple observations from the same telescope, we can then pin down its trajectory. But even better, if we have more data from multiple observatories, we can then get a much higher precision on the trajectory of that asteroid. And by using the exact time, date, and position of those dots, we can send that information to the Minor Planet Center.
Based in the United States, this research institute centralizes the millions of observations made around the world.
What they will then do is connect the dots together to try to determine the orbit of that asteroid. In parallel, they have an automatic process where they will try to determine whether that asteroid has already been detected or whether it is flagged as a newly discovered asteroid.
Every day, the Institute updates the orbits of thousands of asteroids. Each year, the trajectories become clearer. But they still hold surprises.
A big problem with asteroid trajectories is that when you calculate them based on the gravitation of the planets, they don't match what we see.
To explain the difference between real and theoretical trajectories, we need to take into account a tiny force that doesn't affect planets like Earth. It's a complex phenomenon that is studied by an international team at the Côte d'Azur Observatory.
When scientists analyze the orbits of asteroids, they discover that their trajectories are modified by an effect that isn't linked to gravity. This is the Yarkovsky effect. It's fairly simple. This is the asteroid, and this is the sun. One side of the asteroid is heated by the sun, and when the asteroid turns, the heat is transferred to the other side. This heat then acts like a motor and modifies its path.
This effect is impossible to measure precisely from Earth.
The direction and the intensity of this force depends on the composition and on the shape of the asteroid. But it's very important for scientists to estimate that precisely, especially for asteroids that could collide with our planet.
The energy of the sun is captured and reflected by the asteroid, constantly adjusting its path. It can move it away from the sun or towards it, depending on the direction of its rotation. If the asteroid rotates so that the hottest area is slightly towards the front, the thrust will be directed backwards, slowing the asteroid down. In this case, its orbit will shrink and could then cross paths with the Earth. That's probably what happened in 2008, during an extraordinary event that was followed closely by numerous astronomers.
An asteroid is detected using the Mount Lemmon Observatory in Arizona. An alert is then put out because this asteroid is suspected to be on a collision course with Earth. Multiple observatories around the world are observing this asteroid, trying to pin down its trajectory as quickly as possible. The asteroid, now named 2008 TC3, was then predicted to impact the Earth 19 hours later.
Observatories calculated that the asteroid would enter Earth's atmosphere just south of Egypt.
An alert is even given to aircraft pilots to look out for it as it comes through the Earth's atmosphere.
All stations. All stations. All stations. This is Cairo Radio on 5517. Imminent collision alert. Asteroid 2008 TC3 will enter Earth's atmosphere over northern Sudan today at 01 hour 49 minutes UTC. Velocity
Finally, the asteroid disintegrated 23 miles above the Earth, a few hundred miles away from the aircraft. For historians and scientists, this was proof of our capacity to monitor extraterrestrial threats.
What's fascinating about 2008 TC3 is that it was the first asteroid to be detected before it entered the atmosphere.
A few weeks later, a mission was launched in the Sudanese desert to collect meteorites from the asteroid. The 2008 TC3 gave scientists hope that ground-based telescopes could detect near-Earth objects even late in the game. But a few years later, an unexpected event would dispel their illusions. In 2013, in the southern Ural region of Russia, hundreds of people witnessed a small, 60-foot-wide asteroid disintegrate in the sky above them. The asteroid had not been detected by any telescopes. As it entered the atmosphere, it released the energy equivalent of 30 Hiroshima bombs. Heat from the explosion was felt nearly 40 miles away. The shockwave destroyed thousands of windows in the area. More than 1,000 people were injured by broken glass, but no lives were lost.
Chelyabinsk made us realize that even a highly unlikely event could happen. That made us question our ability to deal with asteroids, and it reinforced our efforts to discover these objects, particularly in the United States.
In 2016, NASA created the first Planetary Defense Coordination Office.
One of the things that Chelyabinsk taught us is it doesn't have to be a large object to cause damage. In our engineered world, that a small object like that can wreak havoc. Luckily, no one was seriously injured. But imagine had it been a different season and a different time of day, when more people were outside and the weather had been differently, or had it been a little closer. That story would be very, very different. We shouldn't just be watching for the really big ones. We also need to keep an eye out for the smaller ones, of which there are many, many more.
Chelyabinsk prompted most governments to agree with scientists on the threat posed by asteroids.
Asteroids are now on the national risk list for the United States.
The Chelyabinsk event served as a warning shot and encouraged authorities to look into new ways of detecting asteroids. For a long time, tracking asteroids was based on luck or on limited time slots granted by observatories assigned to other research. But the Russian event highlighted the need to have telescopes that were dedicated to detecting asteroids. The European Space Agency devised a low-cost telescope that could cover large portions of the sky each night.
This is the Fly-Eye telescope. This instrument emulates the eyes of the fly. It is composed, as you know, by several small eyes. They give the full visibility of a very huge field of view. In the same manner operate this instrument.
The Fly-Eye's field of vision is much wider than that of other telescopes.
This very huge field of view of 44 square degrees does not exist in the world. The instrument is capable to scan the full visible sky 3 times per night.
By deploying fly eyes in both hemispheres, astronomers have acquired formidable tools for identifying and even categorizing asteroids over the majority of the sky.
It's possible not only to detect an asteroid, but also to calculate preliminary orbit.
But fly eye and all Earth-based telescopes have their limits. They are blinded by the light of the sun, can only work at night, and are hampered by clouds. The American solution to this is a space telescope that can track asteroids full-time. Coincidentally, a recently retired satellite was available to be used as a prototype. NASA launched this orbiter, known as WISE, in 2009 in order to detect planets in other solar systems. At the end of its mission, it was put into hibernation, though it remained in orbit. The search for asteroids brought it out of retirement. Scientists discovered that WISE was still partly functioning. After Chelyabinsk, they put it back into operation, tasked with finding asteroids and comets and renaming it NEO-WISE. NEO-WISE is equipped with a thermal imaging camera that measures infrared rays, in other words, the heat emitted by celestial bodies. This tool is perfectly adapted to detecting and categorizing asteroids.
Well, in an optical image, you see the asteroid as a dot or a streak in the image, and the brightness of that dot depends on what we call the albedo, so how reflective the surface is of the asteroid. And if we have thermal infrared images, this actually gives us a better idea of the size of the asteroid, so we can use this to estimate the asteroid's diameter.
Each day, NEO-WISE orbits the Earth 16 times. Despite its narrow field of vision, it provides a unique perspective of the entire sky. Resurrecting this telescope provides a wealth of data that must be analyzed rigorously. In 2020 alone, it discovered more than 40,000 new asteroids and provided the data to describe around 200,000 more. This is more than all the discoveries made by ground-based telescopes to date.
Currently, we have a lot of asteroids in the solar system. Our count is going for about 1 million, but we have 20,000 of them that come closer to the Earth.
If the risk of a collision is unavoidable, we need to learn how to protect our planet. And according to many scientists, we are currently unprepared.
I believe that with today's technology, there would be no way to avoid a collision with an asteroid detected a year in advance, unless it was something very small.
Scientists need to act quickly. In 2011, the European Space Agency, NASA, and other institutes requested proposals to develop a project to reach a small asteroid and change its orbit within a short time frame. Numerous methods were suggested, but a team from the Johns Hopkins Applied Physics Laboratory won the main contract with their proposal to collide with an asteroid. It's not the only way to change an asteroid's course.
Why would you impact an asteroid and try to move it out of its way instead of using a nuclear device or maybe something a little bit crazier like a gravity tractor where you fly next to the asteroid and you try to use the gravity of your spacecraft to push it out of its way?
In astrophysics lingo, A gravity tractor is a probe that would change the trajectory of an object in space without actually touching it. It would use only the laws of gravity to alter its course slightly. But other possibilities have been proposed.
There are many other options too. People have talked about lasers and other approaches to the planetary defense.
But these solutions lack precision and are complex to implement. Unlike the solution proposed by Johns Hopkins University.
Kinetic impact is a very simple technique. We all know what happens when you hit something. There is a straightforward reaction, and that is the easiest technique to test out.
So the lab set to work preparing a probe destined to crash into an asteroid, the first kamikaze probe. In the space of a few months, they came up with a vehicle that included the latest in space technology. Special motors that allow the probe to accelerate constantly towards its target. Roll out solar panels that harness a maximum amount of energy. And a camera that will be used for optical navigation and targeting. The probe and the project are called DART, for Double Asteroid Redirection Test. As the name suggests, the target is a double asteroid called Didymos.
The Didymos system consists of two asteroids. The main one, Didymos, is about 1 kilometer wide, and they has a small moonlet called Dimorphos that's about 160 meters wide. So we call that kind of a system a binary asteroid system. The orbit of the Didymos system actually gets it really close to Earth. It's characterized as one of the potentially hazardous objects.
The probe's original launch was held up by the COVID pandemic, but took place in November 2021. There are no guarantees that this remote control technology will work. So, to avoid a collision that could have dangerous consequences for Earth, the DART mission is not aiming for the main asteroid.
We're going to the Didymos system. We're going to impact the small moon.
In order to film its own demise, the probe carries a camera that is planned to eject and fly in its wake.
DART has a small CubeSat that we're carrying called LiCiCube. It's provided to us by the Italian Space Agency.
After a journey lasting 10 months and covering 93 million miles, Didymos comes into sight. What seemed to be science fiction has become a reality. Eleanor Adams outlines how the mission should proceed.
We're arriving to the Didymos system about 6.5 kilometers per second. The whole time we're guiding ourselves on Didymos because we don't see the moonlet until about an hour out. So we stop guiding towards Didymos and we start guiding towards the little moon.
At this point, the probe becomes autonomous in order to finish its suicide mission alone. After the impact, the LiCiCube has a mere 100 seconds to photograph the event. The collision is due to take place on the day Didymos passes closest to Earth. Telescopes are focused on the asteroid, but they're not powerful enough to see the consequences of the impact on the moon, Dimorphos. Instead, astrophysicists are forced to make assumptions.
The dart impact onto that asteroid creates a pretty large crater, about a 20-meter in size.
Though not all scientists are in agreement.
We're talking about a crater measuring 20 meters across, but we have no idea because there are so many different factors.
Images of the crater provided by the Lithia cube could be obscured by the debris created by the impact.
All of the pieces come off, and in low gravity, they shoot out in form of a large plume. So some of the ejecta are lost in space. Some, over time, will settle back onto Didymos or Dimorphos.
When the area is clear of all this material, the European Space Agency will launch a follow-up mission using a probe called Hera.
Hera is our life insurance in a way, because it will measure the effects of the impact and therefore will confirm its efficiency.
This mission should finally put an end to the debates.
Hera will arrive on Dimorphos to measure the size of the crater produced by the DART mission. It will measure the deviation produced by this mission, and it will measure all the physical characteristics of the asteroid that DART's impact depends on.
Hera will also carry 2 miniature cube satellites that will perform chemical analysis and take X-ray images of the core of Dimorphos.
By characterizing in detail the physical properties of the asteroid and the crater resulting from the DART impact, we're going to be able to use this information to calibrate our numerical models.
This information will be made accessible to scientists throughout the world to prepare for our planet's defense.
We can use these numerical models to help us predict how to deflect an asteroid in the future.
Beyond the science, these asteroids raise questions about how governments would manage a crisis of cataclysmic proportions. Using preparedness exercises, an army of experts is trying to establish rules of conduct. In the event of a predicted asteroid impact with the Earth, the ethical and economic stakes are so high that only the United Nations has the authority to manage the crisis. It has created a special division called the Office for Outer Space Affairs. Among other things, it is drawing up a set of rules to be adopted if a collision is confirmed.
So in case there would be an asteroid discovered in size of 10 meters, I1 would issue the warning, and this information would be then shared via our Office for Outer Space Affairs to member states. In case of an asteroid assessed to be 50 meters in size, with a probability of an impact larger than 1% over the next 50 years, the Space Mission Planning Advisory Group would start considering in-space mitigation options.
In 2022, our space surveillance system allows us to detect objects larger than 30 feet across, several days before they reach Earth and impact a highly populated area.
Preparedness is obviously very important, and that's why we are trying to link the planetary defense community with emergency response and civil protection communities.
The United Nations provides its member states with emergency response solutions to an asteroid threat, such as sheltering displaced populations or providing reliable information to the general public. It's easy to imagine that the world is united against this threat from outer space. But space ventures are always shrouded in politics. In 2021, in a bid to emerge as a leader in space, China announced its plan to deflect a near-Earth object on its own. The Chinese project is targeting Bennu, an asteroid 1,600 feet in diameter and weighing 78 million tons. Coincidentally or not, NASA has spent millions of dollars sending a probe to this same asteroid in order to take samples. According to China's theoretical plans, 23 Long March 5 rockets will crash into Bennu simultaneously. It's not clear how other states will react to this show of power.
I think when there is a probability of an impact by an asteroid that would affect large populations, countries tend to come together and decide on taking action.
The ongoing climate crisis demonstrates humanity's inability to act in unison faced with a global threat. Anticipation remains crucial. But thanks to giant leaps in space technology, we are better prepared to protect the planet from distant threats than those from within. The Minor Planet Center is now tracking a record number of asteroids. Furthermore, telescopes such as FlyEye and NEOWISE accelerate the pace of detection. Within the asteroid belt, asteroids larger than 300 feet are now all known, and those in the 150 to 300 feet range will soon be catalogued. There is no doubt that small asteroids, such as 2008 TC3 or Chelyabinsk, will surprise us again and could cause extensive damage if they fall in inhabited areas. Fortunately, the lessons of the DART and HERE missions will help us avoid a major impact with large near-Earth objects measuring more than 150 feet across. But in the near future, humanity will not be able to detect and deflect smaller space invaders.